Go ahead.
So the VGA text function has a different range than the VGA pixel. So it's not 640 by 480, it's a more constrained range. If you try to write outside of that, I'll bet the symptom would be a seg fault.
Yeah. Do you know how it maps, or should I just try to dig through the file? Is it actually in the C code, or is that actually, are the lines like mapped on the FPGA? And
Well, it might be in the C code. I hope it's in the C code, and I'm embarrassed that I didn't range check it, but
yeah, because it like I see a shift, but aside there's an offset like Y left shifted by 7 plus X, but
so it is 80 by 40, I believe.
okay. Oh, like a terminal or similar.
Yes, right. Yeah, I think those are the and I didn't. Oh, I'm so ashamed I didn't range check that.
80 by 40 sounds right.
You'll notice that all of the pixel graphics stuff is range checked, and I might have just brain farted that, to use a technical term. Let's see.
Speaking of bugs, another good one that Bruce and I were talking about before folks signed on, I've had to reset a couple of HPSs, which is fine, but I suspect that what's causing that after talking to Bruce is if you write to a non-existent address on the AXI bus. So if, for example, you attempt to write to a PIO port at the incorrect address, Linux will hang waiting for a response. So if you stop getting responses from your ARM, if you can't access it over PuTTY, probably that's what happened. And I'll very happily just go and reset it for you. But it's just good sort of incentive to be careful when you're doing this memory, making sure that you have the right memory address, because it might create a bug that's takes a little bit more time than others to recover from if someone has to go in there and push the button.
There is, if you write to a non-existent address, Linux really doesn't like it, and it permanently halts. According to the only documentation, which is the source code, in the subroutine VGA text clear, it writes a blank to every position, and the range is 0 to 79 and in X and 0 to 59 in Y.
I think the HPS thing can also happen if you have the wrong like range set for your base like range, because that was happening to me. Like I had the right number, but my range wasn't big enough, and it was crashing my HPS.
So that'll seg fault. But did it hung?
Yeah, I just couldn't. I remember Hunter had to go reset my HPS a few times. I think that was why.
So you're writing outside of the span. Should have seg faulted. Interesting.
Anything else? I was walking around 238 this morning, just peeking at all the VGA screens. It looks like most people are making, I see Lorenz plots in sort of various stages of completion, but it looks like most people are on the warpath. But any other issues people want to bring up before we get into stuff? Today's going to be all about lab two material. Okay, well, if anything occurs to you, just interrupt me. But in that case, I'm going to start with stuff. And I wanted to start by just finishing the math that we started looking at last time, whenever that Wednesday. So because it was a lot, I thought I would just sort of very briefly in words walk through what we did last time. to arrive at the ultimate equation that we're going to be implementing. So I'll remind you that what we were looking at last time is the point of the lab is to build a simulation of the surface of a drum. And we model the dynamics of the surface of the drum with the 2D wave equation. And the continuous form of that 2D wave equation is shown here. This is what we started with last time, where c is the speed of sound, u is the out-of-plane amplitude of one of the nodes on the drum. T, of course, is time. X and Y are the two spatial dimensions along the plane of the drum. And eta is a damping coefficient. So last time we started with this equation, and then we wanted to massage this into a discretized form so that we could actually implement it on the FPGA. So we wanted to take this from a differential equation to a difference equation. And we came up with the difference representation for the first derivative by remembering the definition of derivatives in terms of limits and then approximating that for a small delta t to come up with a difference approximation for the first derivative. And then by doing the difference of differences and applying exactly the same formula, we came up with a difference approximation for the second derivative. So this is the sort of the primitive that then gets plugged in throughout that wave equation. Introduced a little bit of notation in order to talk about these things a little more concisely. So the notation that we introduced is some indexing variables in order to specify the particular node that we're talking about. So if we specify node with the index ij, that is to say the node that's in column I and row j. So we can talk about a specific node. And if we talk about that node at time step n, we use the variable n to indicate time step, right? So the present time step we'll say is time step n, and the next time step at delta t later will be time step n plus 1. So the full specification for a particular node will be node I, j, and I subscripted the i's and j's. So we're talking about a specific node ij at a particular time step n. So like down here, we're looking at node ij at time step n plus 1. So with that notation defined, then we took our difference approximation for the second derivative, just rewrote it using this notation, and then substituted this primitive for the approximation of the second derivative back into a few more places in that wave equation. So we substituted in the difference approximation for the second time derivative, and then used two terms with exactly the same form to describe the second derivatives in the spatial dimensions. The only difference being that instead of looking at differences in the time dimension, which is to say differences, n plus 1, n, and n minus 1, we're instead looking at small differences in the spatial dimensions. So I plus 1, I, and I minus 1. So adjacent nodes in the x direction, and then j plus 1, j, and j minus 1, adjacent nodes in the y direction. And then we also have our difference approximation for the first derivative with you'll recall we centered this around time step n, because all of our second derivatives are centered around time step n. So instead of doing u at ij at n minus u ij n minus 1 over delta t, we instead looked at the difference between time steps n plus 1 and n minus 1 over 2 time steps, 2 delta t, which keeps everything centered around the time step n. So this is the discretized form of the wave equation. If you know initial conditions, and if you set your parameters, then you will know everything in this equation except for the next time step, the n plus 1 time steps here. So we solve this equation for the updated state, uij at n plus 1, which is all that we've done here. We've taken this equation and through much algebra, rearranged it in order to solve for the next time step at n plus 1. Introducing a little bit of a parameter which we've called rho. So in the places where c delta t over delta x or delta y squared existed, we substituted in the parameter rho. And you'll recall that we're going to choose our initial conditions and our parameters to make certain that this stays beneath 0.5. If this gets above 0.5, then our drum's unstable. We want a stable drum. Which ultimately led us to this equation. And this is where we sort of ended last time. So this is the discretized form of the wave equation where we've solved for the next time step. So this is a systematic way to update the drum, each node of the drum. If you know the state of each adjacent node at time step n, and if you know the state of the node that you're updating at time step n, and if you know these constants, then you can solve for the next state of that node. And you'll do that for every node on the drum in order to update it between samples. And then we introduced one more little piece of complication, which is this parameter rho. We're not going to make this a constant. We're going to make this a function of the amplitude uij. And I had a small typo last time that I wanted to correct. So I said that we're going to say that rho is equal to the minimum of 0.49 to enforce that stability condition, or some rho naught plus the amplitude uij. Last time I had a plus here. This should have been a multiplication times a gain squared. So in brief, that's what we looked at last time. And I want to sort of start with this today and talk about one more opportunity to simplify this a little bit for implementation. And the way to the simplification is going to be associated with this reciprocal term. So consider the first reciprocal term. Which I'll rewrite here. It is this first term here.
Is G tension just like a constant?
That's a constant, yes. So if we look at this term, if you think about a drum and the damping on a drum, you can expect for eta to be pretty small, right? The damping in a drum is pretty low. It oscillates for quite a while. So if eta is quite small, and if delta t, your time step, is quite small, then this term eta delta t over 2, you can assume is much smaller than 1. So as we talked about before, you should be itching to Taylor expand something like that, right? So you can approximate this first term by the first order Taylor expansion of that term. So we can approximate this with a first order Taylor expansion. So we say that this is approximately equal to 1 minus eta delta t over 2. It's approximately equal to that. So you can implement this equation, an equation which is almost exactly the same as what we said last time, but instead of that first reciprocal term, you can safely approximate that first term with this first order Taylor expansion. In fact, I'm going to share this document with folks, but just to make it perfectly clear. This is the equation that we can implement. And as before, so you can look at this, and it's a lot of terms, but we know what all these terms mean. And the implementation itself like we talked about last time, right? Everything in these brackets is adds, so that's easy. This is a multiply by 4, so that's just a shift. That's easy. Multiply by 2, that's just a shift. With strategic choice of eta, you can make this first term and this term a power of 2. So you could also make these shifts. So the update for each node should require, this multiplication by row will be a no-kidding multiply. So you'll need one multiplier there, and the calculation of row will also require a no-kidding multiply. So when you update each node, I expect that you'll only require 2 hardware multiplies per node. And we'll take a look a little bit later at the hardware resources that are available on this chip. It turns out that you have 174 18 by 18 hardware multipliers available. So if you think about that, 174 multipliers, if you require 2 multipliers per node, you can start to do the math about how many nodes you can parallelize in a single time at a single update before you run out of multipliers. We'll think more carefully about this in a moment. And a requirement of this lab is that you should be able to produce at least 3 different sounds. So you can think about how exactly you want to produce these different sounds. You have a few different options. One option might be to set up different initial conditions, right? We mentioned last time how you might consider a few different geometries for initial condition for your drum. Each of these initial conditions will produce a different sound, slightly different sound. So you might consider setting up different sounds that way. You might make rho naught or even G a parameter that you can change a little bit to change the properties of the drum. Or you might consider making the size of the drum something that's under your control from like a user terminal. And I thought it would be worthwhile, because this is all a little abstract, I wanted to just play an example of what this will end up sounding like. So I have an FPGA hooked up with one of these, a drum simulation, basically a completed Lab 2 loaded onto it. And I just wanted to play this so that you can hear it. Can you hear this? So do you hear when the drum is first struck, it sort of goes boom, right? That's the nonlinear row. So you'll be listening for that. We'll be listening for that effect in your drums. And I can make the drum smaller here, and it'll produce slightly different sounds. If I make it bigger, it turns out than 172. Say I make it 180, then I can't complete a whole drum in one sample, which produces these sorts of artifacts. But 172 is about the limit. So some things to think about as you're doing this is, well, okay, let's just continue this conversation, and then I'll talk about that. So required resolution. The question is, how many bits do I need? You know, in order to, how many bits should I use to represent the state of each node in order to capture all of the sort of audio effects that I want, but without carrying too many? And it turns out that fixed point 1.17 sounds really nice. You can experiment with this. If you carry, so this is 18 total bits, right? If you attempted to use less bits, say you used 10, the symptom is the drum dies out really quickly, and you don't get much sort of the nice ringing that you associate with drums. If you carry as few as 8, you get silence. It seems to be the case that with that few bits, the wave doesn't even propagate across the surface of the drum. So 1.17 seems to be the right number. The other nice thing about using 18 bits is it allows for you to exploit the 18 by 18 hardware multipliers that are on the FPGA. So this is what, you can experiment with this, of course, but recommend 1.18, which means that the amplitude of any node on your drum cannot exceed ±1, or you're going to overflow your drum. So you need to be very careful about initial conditions for your drum so that you're not giving it so much energy in the initial conditions that, you know, when it drops from your initial conditions to the other side and back and rings, that you're not exceeding ±1 to cause an overflow. The symptom of that might be, what would the symptom of that be? Either silence or a really loud hissing at you. So as you're working on this, it might be a good idea to sort of keep the volume low in your headphones as you're debugging and incrementally turn it up, just so that you don't smash your eardrums with really loud hissing when you accidentally overflow your drum. Okay. Any questions? I'm just marking off my list. There's a number of things I want to go through today, so I want to make sure I'm not missing anything.
Early on, I did a MATLAB simulation with effectively infinite precision, and 1.17 converged within 0.1% to the double precision MATLAB in terms of the eigenfrequency, in terms of the frequency and the amplitude distribution.
So I'm just going to make a note to be cautious about overflow. Keep your headphone volume low while you're debugging. Okay. So the next thing I want to think about is thinking about parallelization. So if we look at this equation, right, you'll build a state machine for each node that calculates this update. You know, so it'll be in all likelihood, you'll build some module that takes as inputs the amplitudes of all of the adjacent nodes and takes as an input the amplitude of the node that's being updated at the current time step, and produces as an output the amplitude of that node in the next time step. So much like the module that you built for lab 1 took in your states X, Y, and Z and output the updated states, it's going to be a version of that kind of module, some combinatoric module that takes in everything on the right side of this equation and then returns the updated state. So the amount of cycles that it will take for you to update a single node is not going to be very many. You know, you may be able to update a single node in, depending on the size of your state machine, like 2 to 5 cycles on the FPGA, right? 2 to 5 maybe rising edges of the clock 50 line. So, and also recall that we're producing audio samples at 48 kilohertz. So let's just suppose that you're using the clock 50 line to clock your state machine, right? So you have a 50 megahertz clock, and suppose that you are able to update a particular node in 2 cycles. Well, if you have a 50 megahertz clock, 50 million, and you're sampling at 48 kilohertz, that means there's something like right about 1040, 1041 cycles of the FPGA between each audio sample. So if you were to do the simplest version of parallelization, which is to say, if you were to take your state machine for updating a single node like this one and make a bunch of copies of it and update them all in parallel and then wait for the next audio sample before you update them again, you could update each of these nodes in parallel in 2 to 5 cycles of the FPGA, which means the FPGA would be sitting doing nothing for over 99% of the time. And if you're trying to build the biggest drum that you can possibly build, you want to fill all the cycles, as many of the cycles as you can fill between the 48 kilohertz audio samples with calculation. You want to be updating as many nodes as you can in that time before the next audio sample comes in. So what that means is you want to build some sort of a state machine that combines serial processing with parallel processing, right? So you don't want to just parallelize individual nodes, because if you're only parallelizing individual nodes, you're going to spend most of the FPGA's time doing nothing. What you should be thinking about is building a state machine that perhaps spends those 1,000 cycles walking through a tile of nodes. So suppose, for example, we're thinking about this tile of nodes shown on the screen. Maybe the state machine, maybe the hardware that you parallelize is logic that systematically walks through these nodes, updating each one, paying attention to the interfaces here, but updates each one, as many as it can in 1,000 cycles, and then you make many, many copies of that tile in order to build as many nodes as you possibly can. Right, so you think about one state machine that walks through serially as many nodes as you can in 1,000 or so cycles, and then you take that logic and you copy it over and over and over again as many times as you can until you run out of hardware. And the hardware that you're going to run out of, it might be multipliers, it might be logic elements, it might be memory, it depends on your specific implementation. But you're going to fill the FPGA with as many of these things as you can. Now it turns out, and I'll talk about this more or less next time, but I'm going to talk through the strategy for parallelization that has resulted in the largest drum sizes that we've seen in this class so far. And it turns out that it's not actually a sort of a tiling of square sets of nodes like this, but instead parallelizing across columns. So you give each column its own memory block, and then your state machine can walk up the column and do in parallel across all of the rows. That's created the biggest drums that we've seen so far, and I'm just kind of teasing that. I'm not going to go over that in detail today. I'll go over that in detail next time. That's produced drums with, God, hundreds of thousands of nodes, right, Bruce?
On the order of 100,000.
I think you're on mute.
I should be off now.
Yeah.
On the order of 100,000 by the time you get the overhead. But that's enough nodes that the drum is almost subsonic. Almost can't hear it because it's too low a frequency. Which is kind of cool.
Yeah. If you have headphones with nice bass, you'll probably get nicer feedback about your drum sounds. I noticed this when I was prototyping at home. I have a speaker system with a subwoofer and then little chirpers, and you can control them individually. If you turn off the subwoofer for very large drums, you don't get much audio out of the little chirpers. So if your headphones are able to have quite a bit of bass in them, you can hear a lot more sounds. I've been thinking about this too. I want to do a 4760 project that simulates whale song. You need a lot of bass for that. So I've been trying to think about how to get bass. In any case, so let's look at, so these are the sorts of, I'm going to talk in a lot more detail about the parallelization scheme next time. But start thinking about parallelization and balancing these resources. I thought it would be instructive to take a look at the resources that are actually available to you. So I'm going to go to course website here. And we can take a look at, for our particular board. This link exists elsewhere on this site, but I know it exists here. So we are using this particular model of the Cyclone 5. So you can see that this is telling you all of the resources that you have available on this board. So 85,000 logic elements, 128,000 registers. That's not that many. So what that means is if you attempt to only use registers to store state information for your drum, you're not going to be able to build a very big drum. You need to instead use some sort of memory, and I recommend that you use this M10K memory. You can see that on this board we have 3,970 kilobits of M10K memory. So that can store a lot of state information. And I'll go through some examples about how you build this and how you manipulate it. But this is the amount of memory that you have available. And then you can see some of the other resources that you have available. 174 18 by 18 multipliers, 87 variable precision DSP blocks, which I believe have their own 18 by 19 multipliers in them that are separate from this 174. But I'm not certain of that.
I think that the 18 by 18 multiplier is a subset of the variable precision, partly because the 174 is exactly 2 times 87. So I believe that there are two 18 by 18 multipliers in each variable precision DSP block, which can go as high as 27 bits in one cycle. But I believe it's when you've used up 174 multipliers, you're done.
And I'm going to show you in the next thing I'm going to show you is in Quartus how to open up the compilation reports for when you're compiling your project that will tell you how much of all of these resources your design is using. Because what the exercise is going to be is to compile this. You can figure this out on pencil and paper. It's a good exercise to figure out on pencil and paper, for example, how many multipliers do I think I'm using in this project? And then to compile it and look at the compilation report and make sure that it agrees. But what you'll be doing is looking at that compilation report and saying, oh, I have 4 more multipliers that I can use, which means I can add this many more nodes. And you want to push, you want to exhaust whatever your limiting resource is. So if your limiting resource is multipliers, you want to exhaust every multiplier that's on that FPGA to get as many nodes on that drum as you possibly can. Some other resources I can point out is the number of phase locked loops that are available. I mentioned that at 50 megahertz, at a 50 megahertz rate, you have on the order of 1,000 cycles to play with between audio samples. I'll show you in a subsequent lecture how you can make your own PLL. So you could make a 100 megahertz clock, which gives you more effective samples between cycles. So that does not increase the amount of parallel hardware that you can build. That's constrained by what's actually here on the board. It's constrained by, for example, the number of multipliers. But it allows you to serially walk through more nodes between samples. So with twice as fast a clock, can you build twice as fast a drum? I'll let you think about that. Maybe, right? So these are the resources that we're trying to push. And I'll show you, let me show you in Quartus how to look at these things. So this is the project. This is a Lab 2 project, my Lab 2 project that I just compiled. If I want to see how many resources I'm using, over here in the compilation window, in the analysis and synthesis menu, for example, I can double click on view report. And this is going to pull up the compilation report and show me the resources that my design is using. So you can see, for example, I'm using 2 phase lock loops, 2 because I built a 100 megahertz phase lock loop to try to get more nodes out, and 136 DSP blocks. That is to say 136 multipliers. So my constraining resource here was not multipliers, it was something else. It's actually logic elements, I believe. I ran out of that before I ran out of multipliers. But this is where you can go as your project is compiling to see what resources you're using. Total block memory bits. You can get some more details about your DSP block usage, for example. So it'll show you how many independent 18 by 18 multipliers are being used and the total number of DSP blocks that are being used. And then if you go to the fitter folder here, we can get a similar report for the fitter stage of compilation. And this will show you things like what's your total logic utilization in ALMs, which is what something logic module. I don't remember what the A stands for. In any case, it'll show you how much, what your logic utilization is. It will show you how many RAM blocks you're using, total DSP blocks you're using, total PLLs. Another interesting thing to look at within here is within the fitter folder here, if you care, you can open up the chip planner. You should do this for your Lab 1 project so that you can look at the Lab 2 project and compare them. But what this is showing you is where the fitter has placed all of the hardware within the FPGA. So we can click on one of these cells and it will tell us, for example, that this is a lab. Or we can click another one of these cells and see that this is some M10K memory. And it's kind of interesting to look at how the fitter arranges things within here and about how the hardware is arranged in here. So you can see, for example, the M10K memory is arranged in these stripes. Control shift, doesn't let me zoom out. There it goes. The M10K memory is arranged in these stripes on the board. And for this example, you can see the board is almost completely filled up with stuff. And that's the idea in Lab 2. And you can see where some of the other stuff on this board lives. Up here, this is all the ARM. Kind of interesting. So again, if you care. But while you're working on finishing up Lab 1, pull this up for your Lab 1 project and just look at the total utilization of the FPGA. You'll see that it's not being utilized very much. And it'll give you a point of comparison for Lab 2 when you are really trying to fill this thing up. Okay. So, anything else I want to talk about within the Tortoise environment? I don't think so. Does anyone have any questions about this stuff?
Yeah, I had a quick question actually. So you talked about using 1.18 fixed point multipliers for this lab, but in the previous lab you used 7.20 fixed point multipliers. So I'm assuming that wasn't built using the multiplier. That didn't use any of the multipliers on the chip, right? That was probably built using the logic blocks.
So the DSP blocks do have, Bruce, you can correct me if I'm wrong. I believe that they have 27-bit hardware multipliers in there.
Correct.
So there are 27-bit hardware multipliers and there are 18-bit hardware multipliers. In Lab 1, you used the 27 bits, and in Lab 2, we're going to use a whole bunch of the 18 bits.
The way the logic is laid out is two 18 bits are bolted together to make a 27 bit with some extra logic. So you can do one or the other, but not both. If you look at your report for Lab 1, your compilation report, the fitter report, you will see that you use the number of multipliers corresponding to the number of asterisk signs you put in your code, number of DSP blocks. You will see you're actually using DSP blocks. You don't have to think about it because Hortus abstracts away that level of detail for better or for worse.
Interesting. And the other question I had was, say we have like 187 multipliers. So I kind of got the sense that you guys are recommending, you said for each node we needed to do 2 multiplies. So are you saying use the same multiplier for 2 different, like take 2 cycles to do both multiplications, or like do we divide up the 187 into sets of 2?
I got a question for Hunter. I think you only need 1 multiply per block plus 1 multiply for the whole drum to get row effective. Is that not true?
Yes, that is true. Because the row is not calculated for each node. Row applies to the whole drum. So you can do that multiply.
So you need 1 multiplier per node, but you can always serialize the multiplier and use it over and over again, just like a regular CPU does, just like the ARM9 uses the same multiplier over and over again, as long as you store the results someplace, hence the memory.
Okay.
So the number of multipliers will limit how many nodes you can update simultaneously in parallel. And then the clock cycles limit how many you can walk through serially within a cycle, or between audio samples. But for that serial, when you're walking through serially, you're reusing a single multiplier.
Right. And this isn't like a square drum, is there? So we can try to fit as many rows as possible, I'm assuming.
So that's a good question. Your drum should be, we're going to put some constraints on aspect ratio. Your drum can't be a string, for example.
Okay.
Right? But we will not enforce strictly square, but there will be some limit on the aspect ratio of the drum.
I see.
I believe that the lab says that the aspect ratio has to be less than or equal to 4:1.
Okay. All right, yeah, that's the only question I had. Thank you.
Yeah. And like I said, we'll talk next time about this strategy of a way to think about this perhaps is parallelizing in one dimension of the drum and serializing in the other dimension. So updating a row in parallel and then serially walking up the drum as far as you can get before the next audio sample comes. It's a strategy to think about. But you can do whatever you like. You know, you can tile these things. You can have whatever arrangement that you want. But you'll need some combination.
Just as an amusing aside, this scheme of parallelizing across columns was invented by a student 3 years ago. I didn't think it up. The student thought it up. And it was very obviously the best way of doing it. That doesn't mean it's the easiest way to do it, though.
The state machine for this lab can be a bit complex. And that's maybe the other resource. So you're balancing a number of resources here. You're balancing amount of memory. You're balancing number of multipliers. You're kind of also balancing your time. This is one of those labs that you can really get into and try to squeeze little bits of performance out. And to the extent, you can do that to the extent that you want to do that. There's going to be some base level that the minimum expected performance is you should be able to beat the HPS. So you should be able to simulate more nodes with the FPGA than you could simulate with just the ARM, which is going to require some kind of parallelization.
I believe the specification in the lab with the HPS and getting creative with the arithmetic, you could squeeze about a 30 by 30 drum out of it, or a 25 by 25 with nonlinear row. But you could only, but we're going to require a 40 by 40 or greater.
So this is also almost entirely a Verilog project. You'll control your drum from the HPS. You can, to the extent that you want, really. The only requirement is 3 different sounds. So you can make your drum as configurable as you would like. But almost everything in this lab takes place on the Verilog side. You're doing all the physics simulations in Verilog, and you're manipulating the audio output with a busmaster in Verilog. So the HPS is really just telling it go, maybe setting some parameters, but that's it. So this is almost entirely a Verilog lab. In contrast to this first one, which had a lot of interaction between HPS and FPGA. I wonder if you could you use the HPS to calculate some nodes? I have never tried that. I could, but could you push the limit of the FPGA and squeeze a few more out by simulating some on the HPS and communicating them over in time? I don't know.
If you can do 100,000 on the FPGA, and you can do 30 by 30 on the, that only gives you another 1,000. So it's kind of anemic. It might work, be kind of anemic. More interesting is, to me, is could you bolt 2 FPGAs together and parallelize it across FPGAs? Oh. But Hunter, could you go back to the equation for a minute?
Yes.
Yeah, that one. You'll notice that there's a sum of 4 surrounding elements, and then you subtract the element that you're calculating from that. So in a sense, what this is how different each one of the 4 elements is, how different the element is from each one of its 4 neighbors. The other thing to notice is that you're adding 4 of these together. That means that if each one of them is greater than 0.25, the intermediate calculation will overflow. How would you fix that? Well, remember that add and subtract commute, right?
So think about the order in which you do these operations in order to make sure your intermediate variables are as small as you can manage. And by the way, don't distribute this row. Do this sum and then multiply, save yourself on multiplies by doing strategic, by strategically doing order of operations in this calculation. Okay, we're out of time. We're going to talk a lot more about this next time as well, and probably the time after that. Okay. I will see many of you this afternoon, and I'll see the rest of you on Monday. Have a good weekend.
Hunter, quick question. The lab